at Tsinghua University, Beijing, and he's also the lead guest chair professor of the group on wireless communication networking. He's an honorary professor at I.I.T, Hyderabad, and he has been elected an associate fellow of the Academy of Sciences for the Developing World. And without any further introduction, please.
Thank you. So one of the privileges or pleasures of growing old is that wherever you go, you find that you actually have friends whom you've actually never met before, which is amazing. I think the world is very small and we all have lots of roots. So even though this is my first time I've come here, I already feel like I know many of the people here. So it's a pleasure. So today I want to talk of cyber-physical systems. And let me give you a little bit of the history first. Okay. So there are several paths to this terminology. And one path comes from communication to sensing to actuation. So we definitely are in the era of cellular telephony. And we may be on the cusp of a wireless networking era. And all of us, of course, know about the sensor networks where you can come and connect your favorite sensor. So you can build gadgets which not only communicate but also sense and do computation. And of course, sensing is only half of what you want to do. Sometimes you also want to take action. And if you start closing the loop, then you get these control systems which can be deployed over a network and so on. So there is this path which leads to the reconvergence of communication, computation, and control. The reason I say reconvergence is because actually in the middle of the 20th century, there's actually a nice book by a professor of the history of technology at MIT, David Mendel, who talks about how all these fields came out of the same cauldron in the middle of the 20th century. So, but after that they became more stratified and grew separately, but now again all these fields are coming back. Okay, another path, and which actually is the path that led to the name of cyber-physical systems, comes from computer science actually. So all of us, of course, are familiar with using computers for computation. That's why they were built. But around 1973, computers started interacting with the physical world, closing control loops and so on. And then you need to worry about doing computations on time. And that led to the field of real-time computation. And in the 1990s, there was a lot of work on hybrid systems. So these are systems composed of the interaction between continuous dynamics, differential equations, and logical dynamics of computers. Okay? And people from both these communities actually started congregating by teleconference, plotting how to extract funding for their research from NSF, and created this word called cyber-physical systems, which was meant to signify that it's computers, which is the word cyber, interacting with the physical world. So the interaction of computers with the physical world. And everybody likes this phrase except the Greeks, because they know what the meaning of the word cyber, and it gets very confusing when you start parsing this phrase. But I just want you to think of cyber as computer and physical as the physical world, and its interaction between these two. There is yet another path that you can think about, and that is the third generation of control systems. So in the modern electronic era, you can think of analog control as the first generation. The technology for that was the feedback amplifier. And that technology needed a theory. And in this case, the right theory was frequency domain analysis. And that theory was supplied by people like Bode, Evans, Nyquist, and so on. Then around 1960 was born the field of digital control. And the technology for that was the digital computer. And that also required a theory. And in this case, the right theory was state space design. And I believe that people like Kalman in the US, Pontryagin in the Soviet Union, and so on were there to supply that theory for us. So I do believe that technology drives research efforts, okay, as in this case. But digital control is about 50 years old now. And in the past 50 years, there have been tremendous developments. Okay? So there have been phenomenal advances in embedded computers. I mean 98% plus of all computers are embedded, and it's going to 100%. The whole field of wireless and wired networks was non-existent 50 years ago, and that allows you to build large-scale systems, configure large-scale systems, and manage them remotely and so on. And last but not least, software, tremendous advances in software. I mean, you've gone from things like registers and library to middleware and so on. So tremendous evolution. And all of that is actually leading to a platform revolution. So just like we had a revolution when we went from analog control to digital control, I think there's another platform revolution happening. And whenever there's a platform revolution, you need to examine not only what computer scientists call policy, but also mechanisms. So policy is what should you do with this platform, whereas mechanisms is how should you do it. And both of these need re-examination when there's a platform revolution. And I think that all of this is just in time to save us, save this planet and us. I think it's just in time for the system building era that we are going to face in the 21st century. So as we become aware of resource limitations, environmental limitations, as we want to improve medical delivery and improve our highways and energy supply systems and water and so on, I think these systems that we build will be more and more important. And you can capture these challenges by several phrases: zero accident highways, smart grid, and so on and so forth. Okay, but who cares? Name doesn't matter. So this field intersects many, many areas. And one could talk about, intersection with information theory or software engineering or networking or whatever. What I'm going to do is just focus on a couple of vignettes for this talk. Mostly, the theme that I'm going to talk of is time. I'll talk of timeliness, delays, temporal correctness. And but I will preface a little bit by talking of information. Now, why is time important? If you're using computers just for computation, then the only thing that's important is order. You should do A before B, before C, before D. Okay, it's just event driven. But if you're going to, if computers are going to interact with the physical world, the Newtonian world has a notion of time. Physics has a notion of time. So then your computations and your communications and so on will have to take place on time, otherwise it's not useful. So I think we are moving to greater usage of event come time driven systems. So time is, that's the reason why time is important. I'll touch upon several topics. I'm not sure, I may skip one or two or three depending on how much time we have. Okay. All right, first let me talk about from data to information. People say we are in the information age, and I think that's completely wrong. We are very much in the data age, and hopefully we can get to the information age. So what kind of problems can one dream up? So I think that there's a need for a lot of theories, okay, for generating information, and I want to just touch upon one of them, which is how should networks process information? Okay, so let's consider a very simple problem. Let us say you have some kind of a sensor network. There's a whole bunch of nodes, and every one of these nodes takes a temperature measurement. So you have n nodes, and they take temperature measurements x1, x2 through xn. And there is some fusion node here, or collector node, and that collector node wants to determine the average temperature. So this collector node is not interested in knowing the list of all the temperatures of all the nodes. It only wants to know the average. Okay? Or if you're building another application, say a fire alarm network or something, then maybe the fusion node is only interested in the maximum temperature. Or maybe not even the max, maybe it's only interested in knowing whether the maximum temperature exceeds 100 degrees. Could be just an indicator function. Okay? But the point is that there is some entity, some node, that wants to compute a function of data or measurements available at all the nodes. And it wants this computation to be done by a, in this case I'll take a wireless network of nodes which can also do computations. So we are interested in, so the point I want to make is that sensor networks, therefore, are not, you should not just think of them as data networks, where you simply replace files by sensor measurements. The reason is, in a data network, the routers are not intelligent. And not only that, a router will never look inside the content of your packet, of your email, and say, this is a very boring email, I don't want to send it. Okay? Whereas in a sensor network, maybe a node can say, this is a low temperature, I'm not interested in this low temperature, so I'm not going to forward it. So the nodes in a sensor network can create packets, they can discard packets, they can change packets. So basically, what these nodes are doing is they're taking all the information that's coming to them, processing it somehow, and then disseminating it somehow. And what we're interested in is, what is the right way that a network should process this and extract information that a fusion node or somebody may be interested in. Okay, so how should we process information in network? Now, there have been lots of models of computation, right? I mean, going back to Turing church hypothesis, and so on. What we are talking of here is a computation model which involves wireless networking. Okay, I'm going to just to illustrate possibilities here, I'll take a very, very simple example. I'll just contrast the difference between computing the average temperature versus the maximum temperature. And it turns out that both the architecture and the algorithms for doing these are completely different. So let's start with the average temperature. It turns out that there are n nodes. Then if you create a multi-hop network, wireless network, you can calculate the average temperature at a rate 1 over log n. Okay? So this is the way it scales. And the architecture for doing that is the common sense architecture that all of you would come up with. And what is the architecture? Very simple. Here's your domain, and this domain there are lots of nodes, and there is some fusion node somewhere here. So the first thing you do is you'd break up the domain into cells, you tessellate it, and in each cell there's a bunch of nodes. And what you'll do is you'll add up all the temperatures in a cell, and then you'd pipeline all those total temperatures in a cell along a tree rooted at the fusion node. And it turns out that this is the optimal way to do. So the interesting part is to show that you cannot do better. Okay? And so that's what gives rise to this sharp theta notation of Knuth. So there's a lot of load balancing going on. There's a load balancing of gathering information here versus creating a bottleneck here and so on, and you do this is the right thing to do. Okay? On the other hand, if you want to calculate the max temperature, you can get an exponential speed up. You can do it at rate 1 over log n. And the architecture for this is completely different. And to illustrate that, I'll take a very simple context. Let's just suppose that all temperatures are binary, 0 or 1. So if anybody has a temperature of 1 in this room, that's max. We'll also suppose that just for simplicity, it's not a multi-hop network, it's a simple broadcast network or a co-located network. So whenever anybody talks, everybody hears. Okay? So how would you calculate the max? Well, it turns out that you take advantage of something that communication people know. You have to take advantage of block coding. What is block coding? Block coding says you don't send information bit by bit, but you collect up a huge number of bits, 1,000 bits, and then you process them en bloc and send them. That's more efficient than sending it bit by bit. So this is a notion of due to Shannon. Okay, it's the basis of information theory and communications. Interesting point is that when you're calculating the average temperature, block coding gives you no advantage, at least up to multiplicative constants. Okay, whereas it leads to exponential speed up for the max temperature. So the way you do it is as follows. So the first node stands up and says, I have a temperature of 1 at time 10, time 50, time 100. And then everybody hears it. Then the second node stands up and says, by the way, I can fill in, I have a maximum temperature of 1 at time 5 and 25. And so on, each node stands up and announces fills up some gaps. And it turns out that all these lists can be very, very efficiently compressed, and you can get an exponential speed up. Okay? So here is a very primitive complexity hierarchy. This is the kind of stuff that we need much more research on, but I just want to give you a hint of what the kind of theories that really need to be developed. So let's take what is the most complicated problem in a sensor network. Well, the most complex one is supposing the fusion node is interested in all the knowledge, all the data from everybody. I want to know every temperature reading from everybody. Then clearly the maximum rate at which that can be done is 1 over n. Right? If n people want to talk to me, then the rate at which they can talk is 1 over n. Right? Interestingly, it turns out that calculating the average temperature in a co-located network is just as hard. Calculating the average is the most difficult problem up to order in a co-located network. On the other hand, by taking advantage of spatial reuse, that is reducing your power level of transmission, reusing the spectrum like we do in our cellular system, that is creating a multi-hop network, you can get an exponential speed up. So multi-hopping buys you an exponential speed up. On the other hand, if you want to calculate the max temperature, even in a co-located network you get this exponential speed up, and if you take advantage of spatial reuse you can get another exponential. So this is a very Mickey Mouse story, but this is the kind of stuff that we'll need. Okay? How to relate the kind of information you're interested in and the network to the rates at which things can be done, and determine architectures, algorithms, and so on. Okay, let me move on. I'm going to touch upon a few topics. The next topic I want to talk of is how do you deliver packets on time. Okay? And it is important, I think, in the future, even increasingly so, to provide latency guarantees. See, currently the internet really doesn't provide any guarantees. It's best effort. Best effort means I tried, and if it works, that's great, and if it doesn't, that's it. And even if you talk of guarantees, usually it's just throughput. Your cable company will say I can give you 10 megabits per second, some throughput. But to give very hard guarantees on latencies, we don't have, right? But on the other hand, cyber-physical systems do need guarantees. If you start closing control loops, delay is very important. I mean, just imagine that you're taking a shower and you're trying to adjust the hot water knob, and there's a 2-second delay between the knob and the thing. You can burn yourself, which is called instability, right? And if you're going to control networks, then you have to worry about this. In fact, the FCC has set aside spectrum for vehicular networks. We're going to start networking cars, and if you're going to start doing things in this in automobiles, you better worry about time. But even more so, you can even look at in-vehicle networks. So, was talking to General Motors, and this is a wire harness, and these wire harnesses are very costly, and they're very worried about weight and recalls and complexity and so on. So the thing is that, can we get rid of an average automobile has kilometers of wiring? Can we get rid of the wires and replace it by a base station in the car? So a car may have like about the order of 75 or 100 sensors and about 100 switches. Now this will allow you to upgrade software, upgrade things, add sensors much more easily than if you had to wire everything in a car. Okay? But if you're going to do that, then you better respect time, because even a simple thing like a window opener, if you push your finger there within a quarter second, it should retract, right? So timing is important, let alone anti-lock brakes or spark plugs or whatever, right? Okay, so how do we do that? Okay, and you can think of many other applications. But let me just focus on this thing, replacing a base station in a car, replacing wires by a base station. So let's go back to, so interestingly, we were having a discussion at lunch over the work of Dave Liu. So the field of real-time scheduling was born in 1973 at Illinois, actually. And I want to give you the basic model and the basic results. So, so there are tasks. So there are capital N tasks. And each task is a sequence of jobs, instances, okay? And they're periodic. So jobs of a task arrive with a certain period, okay? And the deadline for each job is end of the period. So for example, this job that came in here needs to be completed by the end of the period, or it's not useful. this job needs to be completed by this deadline. Okay? And typically what people do is they profile these tasks and determine a worst case execution time. So if you start this job at this time, it gets completed at this time. And you want to complete the jobs before their deadlines. Or else, if you don't complete it, you have a deadline miss. And the field of real-time scheduling is very deterministic. You don't want any deadline misses. And there is a classical result of Liu and Leyland. So they came up with this very simple scheduling policy, which is called rate monotone scheduling. And this is present in all your cars and your airplanes and everything. Okay? And the policy is very, very simple. It's a static priority policy. You simply give highest priority to the task with the smallest period. So if jobs arrive quickly, you give priority to that task. Okay? And what they showed was that if the CPU loading is less than a certain number, which depends on the number of tasks, but basically about 70%, if the CPU is less loaded than 70%, then all deadlines will be met. There will be no deadline misses irrespective of phasings. Okay? And not only that, they also showed that if there's any static priority that can meet all deadlines, then this policy can. So it's kind of maximal best policy. Okay, now what we really want to do is lift this kind of a theory to the area of wireless communications. But the biggest challenge has been, always been, how do you deal with unreliability? That is, in the wireless world you have fading and so on. You cannot, it's not deterministic, but yet you want to give guarantees. So what is the right combination of throughput and per packet delay guarantees? And what we want is some guarantee, or you can think of it as a contract between the wireless network and the application. So a contract, what do we need in a contract? A contract is something that the network can deliver, can actually guarantee. Okay? And it should also be something that's useful to the application. So the application can structure what it provides based on the contract. Okay? So what is the right contract? And what I'm going to show you is a theory which looks just right, and there are many, many interesting ways in which it can be extended, and you get sometimes interesting and sometimes even very surprising results. Okay? So let's start with this access point problem. Let us say that you have an access point, and it is catering to capital N clients, and we'll also assume the time is slotted. So this is your time axis, and packets fit within slots. Okay? Now we'll also assume that the wireless channels are unreliable, and just for simplicity in this talk, we'll assume a very simple model. We'll assume Bernoulli unreliability. So if the access point sends a packet to client 1, it is successful with probability P1 and unsuccessful with probability 1 minus P1. Very simple. On the other hand, if it sends a packet to client 3, its success probability is P3 in a slot. Okay? And we'll allow that these channels, the reliabilities of this channel can be different. These PIs can be different. Okay, now we'll assume that we'll suppose that packets come periodically to the clients, okay, at a certain period tau, and the deadline of each packet is the arrival of the next packet. If you have a sensor information, and if new information comes in, then the old one is useless. Okay, so that's the model. And so in this particular trace, this packet so this is one client we're talking about. I'm showing you 3 periods. Okay, and a packet comes in and it's delivered at some time. Here's another packet that came in, delivered. But here a packet came and for some reason it was not delivered. Maybe the channel just failed. Maybe it was busy trying to send some other packet, whatever. It failed and therefore the packet was dropped. Okay? So in this trace for this client, we can say that the throughput is 2/3. That is, out of 3 periods, you deliver 2 packets. Okay? We can say the throughput is 2/3. Now but this is not just ordinary throughput. It is throughput of packets with per packet hard deadlines. It is the throughput of packets that respect a time deadline. So we'll call this the timely throughput. Okay? Now let us suppose that clients come in and say, listen, I want a certain timely throughput. So this client says, I want a throughput of 80%, timely throughput of 80%. So every client requests a certain timely throughput. So this complete problem is then described by a few parameters. There are many clients. There is a period. For each client, there's a certain channel unreliability model, and each client requests a certain timely throughput. Question. So at this point, if this is your contract, the question is, can these requirements be met? It's a binary answer, yes or no. For this set of clients, can you do the job or not? Okay? And we want simple characterization, we want elegant scheduling policies, and so on. So then we can build a rich theory on top of this, and then maybe this can be used as a model for all kinds of protocols and so on. So that's the idea. So I want to show you I'll give you hints of what the theory does. So let's first talk of characterization of feasibility. Okay? First we can calculate the load on the access point. So what is the load? The nth client, how much of the access point's time does it require? That's the load imposed by the client on the access point. Well, that's very easy to compute. The client requires qn packets per period. Each period consists of tau slots. So it requires qn over tau packets per slot. On the other hand, to deliver a packet, it needs to make 1 over pn attempts. Why is that? If I have a channel that's 50% reliable to you, then I have to make 2 attempts to get a packet through. If my reliability is 1/3, I need to make 3 attempts. So the number of slots I need to deliver 1 packet is 1 over pn, and I need to deliver so many packets per slot. So this is the total number of slots per slot that is demanded by the nth client of the access point. So this is the load imposed on the access point by the client. Now, queuing theory or just common sense tells you that the total load should be less than 100%. I mean, you cannot keep the access point busier than 100% of the time. So clearly, that's a necessary condition. If it exceeds 100%, you can't meet the service, right? But is it enough? Is it sufficient? And the answer is no. And this is where it begins to become interesting. And the answer is no, because there's a notion of unavoidable idle time. So how does that arise? Well, that arises because when you do these real-time things, there is no queuing and some new phenomena arise. So let's take a simple context here, an access point serving 2 clients, and the period is 3. Now, at the beginning of the period, there are only 2 packets in the system. There's a packet from this client, a packet from this client. That's all there is, right? Any other packets were either dropped at this time or delivered. If they were not dropped by delivered by this time, they were dropped. So this access point only has 2 clients that it can possibly work on. Let us say that in the first slot, it attempts this client's packet and it's successful. Then there are no more packets of this client. Then it has to turn to this client, and maybe it's successful. Now there are no more packets in the system, and this 3rd slot has necessarily got to be idle. So the point is, there's a certain probability that it will have to take a vacation. It simply cannot work 100% of the time. So you cannot keep busy 100%. Okay? So you modify your things and you say, okay, let's add up the total busy time that I need plus the unavoidable idle time. What is unavoidable idle time? If you finish all your work in a period, then you have to be idle, right? You can calculate the expected idleness. So this is the expected idleness if there are capital N clients. And that has to be less than 100%. Clearly, that is necessary, right? Is it sufficient? No. The answer is no, and because of something else that happens. If you look at this here, let's play the following game. Let us suppose that you could throw away some clients. You had to cater to a smaller set of clients. Now, clearly, if a larger set of clients is feasible, the smaller set of clients has to be feasible, right? Now, is it true that if this is met for a larger set of clients, it is automatically met for every subset? The answer is no. And the reason is the following. This is the busy time, this is the idle time. As you increase the number of clients, the busy time increases. but the idle time reduces. So the total is not monotone increasing in the number of clients. So this left hand set does not attain its maximum when you take the set of all clients. So it could attain its maximum for a smaller subset. So actually you need to go back and check every subset. Okay? So now you say, okay, for every subset of clients, I'll calculate the busy time, which is the time required by those clients, plus the idle time were those to be the only clients that you could serve, and that has to be less than 1. Clearly necessary, right? Is it sufficient? And the answer is yes. Okay? So this is a complete, sharp characterization of exactly what real-time communication can support. Okay? Okay, now this actually is an admission control policy. You just have to check this. If it is, then you can meet all your clients, right? You can admit that flow. Now it looks like this is a complicated condition to check because you need to check for all subsets and therefore it's exponential. But actually not. It turns out that there's a way to reorder the clients and you can actually do this test in linear time. So you actually have a very feasible computational policy for doing admission control for real-time services in wireless. Okay? So that's just admission control. So after you admit all these flows, how do you serve them? How do you schedule them to meet all their deadlines? It turns out that there is a universal policy which is very simple and that will satisfy any set of satisfiable clients. Okay, and that policy is based on the notion of debt. So for every client we'll calculate a debt. Now what is debt? Debt is how much I owe you minus how much I've paid you, repaid you, right? So the debt for client N is how much you promised, so many packets per period, minus the actual throughput that you may have delivered, which could be less. So this is the shortfall in the throughput, and I'm just normalizing it. So this is a delivery debt. So it turns out that we can just order clients by debt. I'll give high priority to clients to whom I owe the most, who have been shortchanged on their throughput the most. And that's almost a static priority policy. So at the beginning of the period, you simply calculate the debt you owe to the clients. You owe a huge debt to this person, lesser debt to this, even lesser to that, and you simply give priority according to debt. So the way this policy will work is first you work on this client, you try to send the packet, maybe it fails. Then you try again and it's successful. Then you turn to the next client, you try, fails, try again, fails, then it's successful. Then you go to the least debt client and maybe it's successful, maybe it fails. Okay, so that's the way it works. So it's a very simple policy. It's almost static priority, just like Liu and Leyland, because you need to simply calculate the debt at the beginning of the period. But it turns out that this is universally optimal. That is, if there is any policy at all that can satisfy a set of clients, then this simple policy will. Okay? Okay, now what's the protocol for operation? Is actually very simple. This is like a master-slave relationship. The access point controls the whole show. So for example, the access point indicates in every slot which client should transmit. Okay? So for example, if you were doing downlink, that is packets from the access point to the client, the way it would work is this. The access point will send the data to the client, and the client will reply back with an ACK. Now notice that the access point knows the state of the system. Because it's gotten the ACK, it knows whether the packet reached the client or not. Now, what is PN? PN is really the probability that this two-way handshake was successful. Okay, that's PN. Both packets are delivered. In the uplink, the way it works is actually you can use the contention-free polling mode of 822.11, for example, PCF. So the way it works is in uplink, the access point sends a poll packet to the client, and the client replies back with the data packet. Okay? Now again, the access point knows that the transaction was successful because it got the data packet. It doesn't need an ACK. Okay? And PN is a probability that both these things were successful. No need for an ACK. So either case can be handled. Okay? No problems. And so it's very simple to implement. I was debating whether I should do this or not, which I will skip. But this is handles elastic traffic, and it has some very surprising results, which say that you can do real-time services without channel modeling and channel characterization, because you can devise a pricing scheme which satisfies things, but I don't have time to talk about it. In fact, when do we end, by the way? Huh? 2? 2 o'clock, okay, fine. Okay, what is this? Okay, let us actually I'll skip this also. I was going to talk of clock synchronization, but we will skip. I want to go to a okay, let's go very quickly. I want to show you some points here, then we'll okay, clock synchronization. I think knowledge of time is very important in these systems for several reasons, okay? And however, it is impossible, so we want to do clock synchronization, okay? As we move to event come time driven computing, knowledge of time is important, but it turns out that it's impossible to synchronize even 2 clocks, okay? So this should be a well-known fact, but it's not. And it's so easy to see that I'll give you a proof of this. So let us say that you have two nodes. This is a reference node, a Greenwich Mean Time, and this is another remote node. And let us say they're exchanging data packets. Now, I'm talking of packet level synchronization, okay? We'll suppose that clocks are linear. So this is the clock on time on clock 1, clock 2, and they're related by a linear curve. The slope of this curve should ideally be 1. They should both clocks should tick at the same rate, but they may not, and that slope is called the skew, and then there may also be an offset. Now, when these 2 nodes exchange packets, we'll suppose that there's a delay, okay? There's a delay D12 when packets are sent from here to here, and another delay backwards. Now, you may ask, why are these 2 delays different? By delay, I don't mean just the electromagnetic propagation delay. I mean the delay from when you timestamp a packet to the operating system interrupts and everything, it goes to the stack, the communication stack, etc., all the way through medium access control. All of that is kind of random, okay? And then it goes to the tip of the antenna, and then the electromagnetic propagation delay. And at the receiving end, that packet has to be decoded, etc., and the timestamp has to be read out. So, and those encoding, decoding operations may take different amounts of time depending on how loaded the platforms are and so on. So generally these delays are different, okay? And at the level we're talking about, these delays overwhelm the propagation delay. Okay, so basically for this clock synchronization problem, there are 4 parameters: skew, offset, delay 1, delay 2. And it is impossible to synchronize these clocks and determine these 4 parameters. Proof is trivial. Let us say that I have these 2 clocks. I send a packet, and the packet is sent at local time S1, received at remote time R1. It undergoes a delay D12. One can calculate what this received time is. It is the sent time plus the delay, renormalized to the coordinates of the remote clock, okay? And if you send the packet backwards, then if you send it at time S2 and it's received at local time R2, there's another formula relating this sent time to the received time, okay? And you can keep sending packets all day long, and as you do, you keep generating more and more equations. So you generate these equations because these timestamps can be exchanged between the nodes. So all these timestamps are known. What is unknown are these 4 parameters, okay? Now, and you need to basically solve these equations. And you cannot, because this, if you subtract this column from this column, you get this column, which means this is rank 3. And from a rank 3 matrix, you can never identify 4 parameters. So it's impossible to synchronize 2 clocks, okay? Now, how do you overcome this? Well, one way is just to assume that delays are symmetric, okay? But that doesn't solve the problem. It just says that if there'll be if the delays are genuinely symmetric, then this is fine, you can solve it. If not, you'll have an irreducible error equal to the amount of asymmetry, okay? But in any case, I want to move on to networks and noisy observations. So let us look at a network of nodes, and the typical way you synchronize clocks is these 2 nodes exchange packets, determine an estimate of the offset between them. We'll just simply suppose that all skews are 1. This is an estimate of the offset, and this estimate has a certain amount of random error, right, with some variance. these two nodes exchange packets, determine an estimate of the offset, and so on. And if this leaf node wants to determine the offset from this root node, it simply adds up the edge offsets. How good is that? Well, basically every time you add up a random variable, you get a certain amount of error, and this central limit theorem tells you that the error grows like the square root of the number of things you add up. So basically it grows like the square root of the diameter. And if you have a random network with say n nodes, then it turns out that we know very well the asymptotics critical connectivity of a random graph, and you can calculate the diameter of a random graph, and it turns out that this error will grow polynomially. So as you build large systems, error grows, and that's not good. So is there any way of having big O of 1? So any way of providing fundamental support to clock synchronization in large networks? And the answer is yes. The way you do it is take advantage of the physical notion of time. So if you add offsets along a loop, offset of 2 from 1, 3 from 2, 4 from 3, 1 from 4, the sum of the offsets is 0, right? So clocks are not just arbitrary. Time is not just arbitrary. It has this relationship which should remind you of Kirchhoff's voltage law, okay? And that constrains clocks. And it turns out, I'll go very fast now, it turns out that you can take advantage of that to create a very simple algorithm which takes advantage of the following fact. When I am talking to you and we synchronize our clocks, I want to take advantage of the fact that there are two other people at the back of the room talking to each other and synchronizing their clocks. So I want to take advantage of the presence of other people to synchronize a clock with my neighbor. How do I do that? Well, because we are all related by loops, there's a lot of constraints that have to be satisfied. And if I embed those constraints in a least square scheme, it turns out that I can actually get big O of 1 error. Okay? So the simple algorithm, which is even more simple than maintaining rooted tree, can give you clock synchronization in large networks. And this algorithm, so this is a kind of a state-of-the-art algorithm which is from Tennessee. This is the flooding time synchronization protocol. This is the error. Here is our algorithm. The error is smaller if you can see it. And if you build, this is actually a 40-node network, actual implementation, not a simulation. You put the clock at one end, and if you build a larger network, it will get even better. Okay. Okay, so I have a challenge here. So I'm speaking of time, but I'm out of time. So I want to move to abstractions and architecture. So I want to make a case that abstractions and architecture are important for the proliferation of technology. And all of us are familiar with this nominal hierarchy of the internet. And this actually has a lot of good properties. It allows segregation by specialization. So if you are a modulation person, you can work at that layer. If you are a graph theorist, you can work at the network layer, and so on. And you're guaranteed that if you worked out the interfaces, then if you put your efforts together, the products will, the whole stack will work, right? Now, over the course of time, there have been improvements to TCP. There has been Vegas, New Reno, whatever. And every time there's a new TCP protocol, all you need to do is change that layer, and then the thing will still work. So this organization allows evolution with time. Okay. Now, there's always a kind of a tension between the performance people and the architecture people, especially in wireless. Okay, they want to take, the performance guys always want to bust the architecture. So there is somebody who always says, hey, listen, if I could expose TCP parameters to the MAC layer, I can do better. But somebody else may say, wait a second, if I expose MAC parameters to TCP, I can do better. What should you adopt? Well, if you adopt both, then you're creating loops, and then you have instability, possibly. Not only that, if you start taking all these shortcuts, you're going to get a ball of spaghetti, which will not be maintainable, upgradable, evolvable, etc. So by maintaining this architecture, you actually facilitate proliferation, which actually drives down prices. And so architecture is also performance, but over the long haul. Okay. All right, all of us are familiar with, I like this phrase due to Valiant, the von Neumann bridge, instruction set architecture, but I want you to think of it as separating Intel and Microsoft, and they don't need to talk to each other, but they conform to the abstraction and everything is fine. Okay. There is no von Neumann bridge for parallel computation, which is one of our big problems even now. and so on. So anyway, so we have these complicated systems which have sensing, actuation, communication, computation, etc. What should be the architecture for these things? What should be the right abstractions and so on? Now what I am interested in is not to make this thing 10% faster. Okay? I'm interested in radically cutting down the design and deployment and debugging time from 1 year to 1 day. So my performance measure is the design and deployment time. Okay? And the way we want to do that is by using standardized abstractions. You know, the last thing software engineers want to do is write software. They want to cut and paste, right? So we want minimal reconfiguration and reprogramming. So you can build these like Lego blocks, hopefully leading to proliferation. Okay, so what is let me describe our lab here. But before that, we have, let me show you a movie. So we have these cars that are running around on this plywood platform. You have these cameras, okay? And I was visiting some of the labs this morning which are modeled along the same way. And then you have vision processing going on over here. And you have all the layers of decision making, control, regulation, set point, generation of set point, tracking, planning, replanning, scheduling, etc. And you cannot see it, but there are lots of laptops here which you can either configure as an ad hoc network or as you can connect them by Ethernet. And each of these laptops drives one of these cars through a dedicated radio frequency, which you can think of as a virtual wire. So this is a completely closed loop system, closed over wireless networking, closed over vision, closed over control. But the thing that I want to focus on is the software. Okay? But before that, let me show you a movie.
The system runs by having closed loop vision system. We have 2 cameras, 1 for each side of the track. Each of those cameras' image is processed by 2 individual machines over here. That information is then transferred to a data server that is located over here, and it gives it to respective cars and their individual laptops. Each of these laptops controls an individual car. To demonstrate what happens when we lose a vision update, I'll just fake it by putting a cover over it. So that car can't be seen by the camera right now. He has an internal concept of where he is, which was wrong at that moment. These cars are just as happy to go backwards as forwards.
This is an O.J. Simpson scenario. There is a car which is trying to run away, driven by my student, and these are 2 cars automatically following in formation, and he's trying to confuse them. Okay. So you get the idea. Let me show you a more socially useful application.
So in this video, we're trying to illustrate the effects of our collision avoidance algorithm. So to show you how necessary it is to have a collision avoidance algorithm, we're going to control the stationary car into a collision trajectory with these 2 cars going in an oval trajectory. So we move car 10 into position, and you'll see that cars 4 and 2 will continue unabated for a head-on collision.
So that's where we are today.
Things turned into a complete mess, and this was a motivation for developing a collision avoidance algorithm. So after some repairs, several months' work, and a restart, we're ready to show you the effects of our collision avoidance algorithm. So once again, we move car 10 into position, and you'll see cars 2 and 4 stop in response to him being in their path. The way the collision avoidance algorithm works is that each car tries to clear an area in front of him and to gain approval to move into it. So as we move car 10 around and into the area that the car requests approval for, you'll see they get denied and then stop. So each of the trajectories that the cars are following continue to evolve. So we can park car 10 in front of them, cause them to stop. But as soon as car 4, in this case, sees another way to get to his appropriate point in his trajectory, he's going to get that route cleared and start moving off in that direction.
Okay, so you get the idea. I'm going to go rapidly here. The architecture for this system is very simple. We build on the standard networking architecture. Okay, so basically we create a system layer which is a middleware. Okay, it's actually a real-time middleware layer. Okay, and that middleware is supported. What we've developed in our lab. It's a real-time middleware, and the application layer is simply a component architecture. So these components, you could have, if you're a Kalman filtering expert, you write a few lines of code. Deadlock avoidance, you write a few lines of code. Image processing, and so on. The dividing line between electrical engineers and computer scientists is electrical engineers are very comfortable with algorithms, but they don't like protocols. Okay, so algorithms we are very happy. Protocols, we want. These components have all the housekeeping. Okay, that's done by the middleware. It's also very interesting. What electrical engineers call non-functional and functional is exact opposite of what computer scientists call functional and non-functional. Okay, so housekeeping would be non-functional for the electrical engineer, but that would be the functional part for the computer scientist, right? So all this stuff has to be done by the middleware. Okay, and in fact you can even migrate components, and then you can have the notion of services, which is clocks and so on. So you can build very complicated applications like this collision avoidance, where there's many interacting applications which are actually functioning. Okay, I'm not going to show you how migration works and how we can control inverted pendulums and all these things. So at runtime, we can change controllers components on an inverted pendulum, which I'll skip. Okay, I want to talk of two challenges. Okay, one challenge and one morality story. Challenge is this. So this is a traffic control application, which let us see. So I cannot. All right. So it's not playing, but basically there's a traffic control application where you cannot see streets, but all these cars go from their homes to their offices and don't collide with each other, run off the roads, or have deadlock. So I want to prove the correctness of the system, and that what we need is a cross-domain theory. So this is the need. When we build these large-scale systems, there are many fields that go into it, right? There's scheduling, there's control, there is discrete event logic, reasoning, and we need a cross-domain theory to guarantee correctness. So for this traffic control application, I may have a mutual exclusion model of a traffic light, and I may have a ball and bin model of the road system, which things like liveness and deadlock avoidance and so on. And then I may have a notion of the physical world, model of the physical world, some dynamics or kinematics for the car, some Newtonian dynamics here, and then some real-time scheduling going on. And what we can guarantee in this case is that these cars then will be safe, no collisions, no gridlock in Manhattan where everybody wants to make a right turn, and everything is fine. But this is a handcrafted theorem for this application. Now when we start building air traffic control systems and more complicated cyber-physical systems, you would like to automate these things. And the big challenge is, how do you do that? Because in many cases these problems are undecidable if you formulate them the wrong way, or doubly exponentially complex. Okay, so but if you know all these domains, you can model it correctly, and that's, I think, a big challenge, temporally correct behavior of large systems. Okay, but my last slide here. So this is so Toyota funded a project for us on intelligent intersections. So back where I live, there's a traffic light here which you cannot see, but it's kind of useless because there's nobody there on the street. And at nights, in the suburbs, evenings, it's useless. So can we get rid of the traffic light and simply have packet exchanges between cars, which negotiate the traffic light, thereby reducing fuel consumption, lowering traffic delays, and it turns out that if you get it to the human being, you can even improve safety. Okay, so this is actually not a simulation, this is a trace of a provably correct system. I'm not sure you want to drive in these cars, you may get a heart attack, but this is the way the system will work. Nobody stops. It's provably safe, okay? They're making minute adjustments to their speed and doing packet exchanges. There's a nice hybrid architecture, all kinds of things. Okay, but let's think of the larger context. So this is a slide from a talk that Frank Kelly gave at StockNet 2006, which is actually from some other work here. What we are plotting here, the x-axis, the y-axis is the time spent by people to drive to work. Okay, there's 1 hour here per day. What we are showing here is what is shown here is several communities, African village, Tokyo. They're stratified by GDP. So across geography, across wealth, every dot represents the average amount of time that people in that community spend commuting to work every day. And what you see is that by and large they all have decided to travel about 1 hour per day. And what is very interesting is that there's nobody here. People don't like to live too close to where they work. I don't know why. Okay, but so somehow human beings have decided some time back, long time ago, that 1 hour per day is the right amount to spend commuting to work. So if you're a pedestrian, you live like 2 miles or a mile away from work. If you have a horse, you may live 10 miles away. If you are in Los Angeles and you have highways, you may live 50 miles away, right? No matter what, they spend 1 hour going to work. So if that is a human sociological invariant, then if you make it easier for them to go from place A to place B faster, then what will be the consequence? They'll live further away. Okay. So the question is, we have right now the technology to build these systems, right? We have nodes that can compute, communicate, sense, actuate, do everything. But the challenge is, what is the system that we should build? Should we do this? No, that's not the answer, okay? Maybe we should think of congestion pricing or something, right? So I think an important thing to keep in mind, especially for students, is what is the right problem to solve when we have all this technology. And I'm going to stop there. Thank you.